This is Pre-Calc, Section 4.2, Rational Functions and Graphs. In Section 4.1, we already did some rational functions and graphs. However, those were specifically ones that could be looked at in terms of 1 over x or 1 over x squared and doing some sort of transformations on those. There will be a step-by-step process of things we have to look for before we do the graph. So the first thing we want to look for is any asymptotes. Vertical asymptotes are very easy to find. They are found by setting the denominator equal to 0 and solving. So if we take this one right here, I set that denominator equal to 0 and I solve. The reason I set the denominator equal to 0 is you're not allowed to have 0 in the denominator. So we need to find any values that create 0 in the denominator. Solve this by factoring. Set each of those equal to 0, and we will get -1 and 1. Those are our vertical asymptotes at x equals -1 and x equals 1. And these are equations, so you do need to write x equals -1, x equals 1. Now, there is a relationship between the domain and the vertical asymptotes. Wherever you have a vertical asymptote, we are going to throw those numbers out of the domain. So one way to write the domain is in set builder notation. It is all x such that x does not equal -1 and 1. But MATLAB is going to want you to write this in interval notation. But for some people, it's easier to do the interval once this is here. And some of them even like to do like a little graph right here. Put a hole on both of those because -1 and 1 are not part of this number line. Then you can see what your interval notation is. It's from -1 to from negative infinity to -1, union with -1 to 1, union with 1 to infinity. And what that does, it's saying our domain could have been -infinity to infinity, but we have to exclude those values, and that's why it ends up with that answer for the domain. For your horizontal asymptotes, you want to use this chart that we had in college algebra. If the numerator degree is less than the denominator degree, which is the case right here, the numerator degree is 1, the denominator degree is 2, then automatically your horizontal asymptote is the x-axis, which is the line y equals 0. Another possibility is that the numerator degree equals the denominator degree. It is the lead coefficient in the top over the lead coefficient on the bottom. So this is just 2 over 1, which would be 2. So the horizontal asymptote for this would be y equals 2. And if the numerator degree is greater than the denominator degree, there is no horizontal asymptote like this one right here. So you do need to memorize that chart. So here's another situation. If the numerator degree is exactly 1 more than the denominator degree, then you have what's called an oblique asymptote. Another name for oblique asymptote is slant asymptote. So instead of it being straight up and down or straight left and right, it'll be at some sort of angle. It will be a slant. So the first thing you look at is the degree here. Is that the situation here? Is the numerator degree exactly 1 more than the denominator degree? No, it's not, which says there is no oblique asymptote. Vertical asymptote, we set the denominator equal to 0 and solve. And the way to solve this is going to be to factor it equal to 0. Has to be 2x times x in the front. To get a 3 in the back will be a 3 and a 1, but I've got to place these here and here, with the 3 being positive and this being negative. Set each factor equal to 0, and we get 1/2 -3. So our vertical asymptotes are x equals 1/2, comma, -3. Horizontal asymptote, look at the degrees. The degree in the numerator is 1. The degree in the denominator is 2. The numerator degree is less than the denominator degree, so automatically it is the x-axis, which is the equation y equals 0. Then I do the domain. I like to get the asymptotes out of the way first. You obviously can do this in any order you want, but once you have the vertical asymptotes, naming the domain is very easy. You can do the little number line thing like I did a minute ago. Put -3 and 1/2 on the number line. Put holes there because those are the numbers that are going to be excluded. And then you can name your domain as -infinity up to -3, union from -3 to 1/2, and then union from 1/2 to infinity. And all of those do have the curved parentheses, not the brackets. Same set of directions, naming all of these things. Take a look at your denominator. Set the denominator equal to 0 and solve, which gives us x equals 2. So we have a vertical asymptote at x equals 2. Horizontal asymptote is where I take a look at the degrees, and this is where I have the numerator degree exactly 1 more than the denominator degree. That says there is no horizontal asymptote, but there is an oblique asymptote. You cannot have both horizontal and oblique. So we threw out the idea of a horizontal asymptote because the numerator degree is greater than the denominator degree. But specifically, the numerator degree is exactly one more than the denominator degree. So now I have to do some long division. With x squared plus 1, I need to supply a placeholder here, so I put plus 0x plus 1, and I start my division. X goes into x squared x times. Come back and multiply x times that whole thing is x squared minus 2x. Draw the line, change the signs, which makes the x squareds go away. 0x plus 2x is 2x. Bring down the 1 and begin again. X goes into 2x 2 times, which gives me 2x minus 4 when I come back and multiply. Draw the line, change the signs, cancels out the x, and I get a remainder of 5. The remainder of 5 gets thrown out. Your oblique asymptote will be y equals, because it's a line, the asymptote is a line, equals this answer up here, x plus 2. We have to talk about something called points of discontinuity, also known as holes. This has not been an issue yet, and here's the deal. A rational function must be in lowest terms before we can identify asymptotes. I haven't had to mention this before because all of the functions we've done have been in lowest terms. But if there's a common variable factor in the numerator and denominator, then the rational function's not in lowest terms. So we've got to get it in lowest terms, which means factor the top and the bottom here. The top is the difference of two squares, so x plus 2 times x minus 2 over x minus 2. So you can see now that it's factored that this function was not in lowest terms. So now that we have this factored, I can cancel the x minus 2's, and I just end up with y equals x plus 2. That means that this negative 2, since it canceled out, is not a vertical asymptote. It is not a vertical asymptote, but it is a point of discontinuity because we still have to look at the original function and look and say, hey, the denominator is not allowed to equal 0. So because of that, we have a hole at x equal to 2. Now, it's almost as if we were doing the asymptote. To do the vertical asymptote, you know, you take the denominator, you set it equal to 0, and you solve. That's how I get x equals 2. But you have to call it the right name. It is not an asymptote because that x minus 2 canceled with the x minus 2 in the top. But it is a hole in the graph. And I'll show you a picture of the graph in a second. So vertical asymptote, there is none. There is not a horizontal asymptote either because once this cancels out, all we have is x plus 2. So there's no horizontal asymptote, nor is there an oblique asymptote. Even though in this form this was one more than this simplifies into just this equation, which is this graph. That's a line. And notice we have a hole at 2. All right, we have to be able to look at some graphs and identify asymptotes. So just looking at the graph, you can see this dotted line right there, and that is the horizontal line, y equals 2. So you have a horizontal asymptote at y equals 2. Same idea, you have this dotted line coming right through here at x equals 3. That is a vertical asymptote. Do you see any slant lines there? And the answer is no, so there are no oblique asymptotes. And now that I have the vertical asymptote, I can do the domain. It is negative infinity, right on up to 3, union with 3 to the other side. So our domain is coming in from negative infinity all the way up to this wall, if you want to think about it, at 3, and then it picks up again from 3 going to the right. Now you can see that you do have a slant line there. You do not have a horizontal asymptote drawn. You have a vertical asymptote drawn at x equals 1. There is this oblique line. Now this is kind of hard to see. Be sure on MathLab that you blow it up so you can look at it. To name the equation a line, y equals mx plus b, we need a y-intercept and we need a slope. The y-intercept is right here, which is 2. Then to get the slope from the graph, I just have to count to get from a nice, neat, what I call corner point to another corner point. So this is up 1, 2, 3 over 1, so the slope is 1. So this is the line y equals 3x plus 2. And that is your oblique asymptote for this graph. Name the domain, going back to the vertical asymptote, is from negative infinity to 1, union with 1 to infinity. You should be able to recognize that even though there's not a line drawn in there, that this curve is snuggling up to that horizontal line, which means the horizontal asymptote is the line y equals -4. Those numbers are hard to see. That's -2 right there. That's -4 right there. There is no oblique asymptote. There's no sideways slanted line. Nor is there a vertical asymptote. So that's all you have is that horizontal asymptote. Because there is no vertical asymptote, that's going to make your domain from -infinity to infinity. All right, we want to graph the rational function and name all of these things to be able to get a decent sketch. Even though domain is listed first, I don't do it first. Vertical asymptote, we know to set the denominator equal to 0, but double check, is there any reason we have to worry about holes? And the answer is no. There is no factoring, there is no canceling, so I can set the denominator equal to 0 and solve. That factors as x plus 3 times x minus 3 equal to 0, which will give me vertical asymptotes at -3 and 3. Horizontal asymptote, we want to look at the degree of the numerator compared to the degree of the denominator. The numerator degree is 1, the denominator degree is 2, so the numerator degree is less than the denominator degree, which makes the horizontal asymptote the x-axis, which is y equals 0. If there is a horizontal asymptote, there is no oblique asymptote. I could go ahead and name my domain right now, but I think I'll wait and get the graph drawn a little better. The x-intercept, recall to find the x-intercept, you want to set the whole function equal to 0. So set this whole function equal to 0. But now think about something. If this fraction is equal to 0, what's making it equal to 0 is just the numerator. So the shortcut for finding the x-intercept is to set the numerator equal to 0 and solve. Divide both sides by -6 will give you x equals 0 as your x-intercept. But we want to write that as the ordered pair 0, 0. The y-intercept is where you plug 0 in for each of these x's. So if you put 0 in for x here and 0 in for x there, you also get 0. So in this case, our x and y-intercept happen to be at the same point. So let's get some of this drawn. My vertical asymptote, I have at -3, which is right here, and another vertical asymptote at +3. I have a horizontal asymptote at the x-axis. Let's pull that up a little bit. I have a x-intercept and y-intercept right here at the origin. It is possible for the graph to cross the horizontal asymptote. It cannot cross the vertical asymptote. So I have this so far. There's nothing else here that I can graph. I can go ahead and name the domain. The domain is going to come in from -infinity to -3, union with -3 to 3, union with 3 to infinity. Now, to find out what's going on for the rest of this graph, we need to do what's called domain intervals to complete a test chart. You might remember from college algebra that we actually did a t-chart where we pick numbers. -1, do the arithmetic. -2, do the arithmetic, etc. But there's another way which is a little bit easier, and that is to put some pertinent numbers on a number line. And those numbers are your vertical asymptotes and your x-intercepts. Just so happens our x-intercept and y-intercept was the same place, but it's only the x-intercept that has to go on that number line. Then we're going to look at this like we did with the polynomial inequalities and do some test values just related to the signs. In other words, positive or negative. So a value over here to the left of -3 would be something like -4. If I were to put that back into the original equation, let's erase this. If I were to put -4 into the top, -6 times -4 is a positive. Put -4 into the bottom, that would be 16 minus 9, which is a positive. A positive divided by a positive is a positive. So this region is positive. Something between -3 and 0, I'll pick -1 and do the same arithmetic. Put -1 right here. -6 times -1 is a positive. -1 squared is +1, minus 9 is a negative. and a positive divided by a negative is a negative. Between 0 and 3, I'll pick positive 1. Negative 6 times positive 1 is a negative. Put it in the bottom is also a negative, and a negative divided by a negative is a positive. So see, doing this with just the signs, you don't have to worry about being real fancy with your arithmetic. Pick something to the right of 3, I'll pick 4. Negative 6 times 4 is a negative. Put 4 in the bottom, that'll be 16 minus 9, which is a positive. And a negative divided by a positive is a negative. Now, what good is that? That's telling me in this region, in the region to the left of my negative 3 asymptote, that it is positive. It is above the axis. So it's going to give me a curve like this. In between here, in between negative 3 and 0, it is a negative region. So it's down here somewhere. All of this is down here. Between 0 and 3 on this side of the intercept, it is positive. That tells me this has come up this way. And over here to the right of this red asymptote, it is negative, which means this curve looks like this. And you can verify that by typing it in your graphing calculator. Be sure if you type this in the graphing calculator that you do negative 6x over parentheses x squared minus 9. One thing to add that I didn't explain in the middle of this, I said it is possible for your curve to cross the horizontal asymptote, but there is a way to know if it's going to cross the horizontal asymptote and where it would cross the horizontal asymptote if it does. And the way to find that is you set the function, the original function, equal to the y value of your horizontal asymptote, call it b. So for this function, I have negative 6x over x squared minus 9, and I set that equal to my horizontal asymptote, which was 0. So this is very easy to solve. They're not always so easy to solve. Remember, if a fraction is equal to 0, we really only have to look at the top equal to 0. So negative 6x equals 0, divide by negative 6, and we get x equals 0. That little process tells me that my curve will cross the horizontal asymptote, and it tells me it will cross at 0, which in this case happened to have already been our x and our y intercept, but it's not always the x or y intercept. So that's a nice little test you can do on any of these to see if your curve will cross the horizontal asymptote.